How's everyone doing? Hope you all are doing alright today. So, do you have any questions today? Or how are you doing with the material? So, no questions so far? Shall I make any progress on the matrix stuff? Mm-hmm. Good so far. Good. I do hope the matrices are making a little more sense after last Wednesday's class. Did you all gain any insight about the depth to which you would be needing to do that on Thursday? Okay. Well, hopefully that was helpful between those 2 days. So, today we'll go back to Chapter 2. I still needed to cover Section 2.4, and I still needed to assign no homework for 2.1 and 2.2. But now that it's been a week and a half or two since we covered that stuff, I feel real bad assigning that homework at this point, so I don't know. I'll probably assign some, but maybe not a whole lot. Maybe that'll be the compromise. It will only be like 8 or 10 questions versus 15 to 20. So, anyway, theoretically, if I ever get to assign homework. Alright, so section 2.4 is on linear inequalities. Now, linear inequalities basically is talking about solving equations, solving problems where rather than having an equation, we actually have a less than or a greater than sign, or it could be also equal to, but greater than, equal to, less than, equal to, that kind of thing. And we're looking at the one-dimensional case here, and I wonder if we ever cover the two-dimensional case. So I think that would be more interesting, but or helpful, but I might go ahead and incorporate it into the lecture. So, but we'll start off with what I call the one-dimensional case, where we only have one variable. The first thing we want to do is establish how to write the inequalities and how to graph it on a number line, first of all. Like for instance, if we said x is less than 8, here's 8, and if we say less than, we'll shade everything to the left, of course. And then we'll leave an open circle where 8 is, because whenever we say less than 8, it means everything less than 8, but not including 8 itself. Now we contrast that in the situation where we say x is less than or equal to 2. We'll go ahead and put a solid dot at 2 rather than an open circle. We'll still shade everything to the left. Okay. So that's the difference between less than and less than or equal to, and we actually see a similar thing if it's greater than or equal to. I don't usually make a whole lot of numbers on my inequality graphs here. Usually I just include 0 for reference, and then whatever number is important besides that, which is the 8 or the 2 or the negative 1. Okay, and if we said x is greater than or equal to 4, shade the 4, and then everything to the right. Okay, pretty straightforward stuff. Now, when we're solving inequalities, there are a few. Well, one concern in particular is different than when we work with equations. And that is, specifically, if we multiply or divide by a negative, we change the direction of the inequality. Okay. So if we have something like negative 3x is less than or equal to 24, well, we would divide both sides by negative 3, naturally. And this would give us the inequality x is actually greater than or equal to negative 8. Okay. So when we divide it by a negative number, we change the direction of the inequality. Now, beyond that, the same operations that we use in solving linear equations is also used to solve linear inequalities. For example, if we have 2x plus 7 is greater than 5x minus 8. There we go. One thing I would always stress here for inequalities that we don't necessarily have to do for equations is make sure the x is on the left-hand side. We can solve for the x on the right-hand side, but we do have to pay careful attention to how we write our solution. Let me show you an example here. Let's solve for where x is on the right. So we would have to subtract our 2x. Now we get all of our x's to the right-hand side of the equation. And we'll go ahead and add the 8 over after that. And of course, after that, we would divide by 3. Now, you'll also notice that at no point do we multiply or divide by a negative, and so we don't have to worry about that rule in this case. We just end up with 5 is greater than x. But probably the most helpful way that we can express inequalities is where x is on the left-hand side. There's one thing to say that 5 is greater than x, but what does it tell us about x itself? That's why I always like to have x first. So when we can say x is greater than or less than a number, we know exactly what it's referring to. So if 5 is greater than x, if we were to switch that around to where we had x on the left and 5 on the right, what sign would we have in between? Greater than or less than? So if 5 is greater than x, x is what to 5? Less, yeah. We can kind of think of it as a mirror image now, because if 5 is greater than x, then x must be less than 5, looking at it from the opposite direction. And I drew that line there to fill in the blank. It looks like an equal to sign, so I apologize for that. That's my bad. I drew the line there saying we were going to fill in the symbol, and now it looks like an equal to sign. Yeah, I don't mean to confuse you. And then, of course, we fill in or sketch our solution there, which is everything less than 5. So put an open circle at 5 and shade it to the left. Did we talk about interval notation at all? Interval notation written as kind of an ordered pair, but we're saying we're covering everything from negative infinity up to 5. No. Okay. Ignore that for now. We'll get to it eventually. Sorry. It seems like I think I already talked about it in both algebra and calculus classes. So I've used it for one reason or another, but I haven't in here yet, so I'm sorry for getting them mixed up. Yeah, so we'll come back to that concept, but it's directly related, and you can probably see the connection here to the number line that we graphed. But that would be the next logical step, is to be able to write it as an interval. So we'll follow up this section with that discussion. Okay. Let's do another example. Okay, so here we have x minus 3 is less than or equal to 2x plus 5. Really the same approach. We just need to get the x's to one side and the constants to the other. And again, usually it seems like there's an easier direction to move everything, although really we have a lot of flexibility in what we do. The main thing is, like I said in the previous example, we want to end with x on the left-hand side and a number on the right. Just whatever it takes for us to get that inequality correct in between is fine, as long as we're getting that correct. So, but more conventionally, I think generally speaking, it's easier just to keep our x's on the left and then our numbers on the right. So we would take our 2x and subtract that over. So it would be negative x minus 3 less than or equal to 5. We could then add the 3. So negative x is less than or equal to 8. Well, how do we make a negative x into a positive x? Erase the negative sign. That's one way we could do that. Let's think about it in terms of maintaining equality, or inequality in this case. I mean, what operation would we have to do to erase the negative sign? We could add a positive x. And if we did that, though, that'd move x and 8 over to the same side. We don't want to move the terms. We actually like them where they are. We just need this to be a positive. Could divide both sides by -1. Good. If we wanted to, we could also multiply both sides by -1. It would have the same goal. So if after we divide by -1, what is that going to give us? If you want to type in less than or equal to, just do less than equal as separate keystrokes, I guess. Generally, that's how we accept it when the actual sign is not an option. X is less than or equal to 8, -8. Is that right? It's almost right. Greater than or equal to, yeah. Yeah, -8. Again, we divided by a negative, so we have to change the direction of the inequality as well. Okay, so greater than or equal to -8. If we draw our number line, -8 would be left than 0. We draw a solid dot and then shade to the right. Okay. Now, in each of these problems, we just had a single inequality. It is possible for us to have what's called a compound inequality. Let me show you what that looks like next. So this is what we mean by a compound inequality. We actually have two different inequality signs here, and they don't have to be the same. Although, in this case, for the compound inequality, they'll always be less than, although they may also be equal to. And the reason that we always use less than or equal to is because this number is presumptively smaller than this number. So we maintain that difference between them. In this case, we don't normally worry about a negative number, the division, because that would change it to where everything's greater than, although the same principles would still apply. The other thing that has to be accounted for here, because really what we're looking at is two different inequalities kind of merged together, is that whatever operations we do has to be done to all three pieces of this compound inequality. Okay? So, yes, they will always face the same direction. Now, so the other thing besides this one is, in addition to that, move that Each operation is applied to all three pieces, or all three parts. And the goal, so we do need something to work towards here. The goal is to get x by itself in the middle. Because if we can get this just to be a plain x, then these two numbers on the other side are the boundaries for x, or the that's what x will be between, based on the compound inequality. So we think about this and we say, okay, well, what are we going to need to do to get the x by itself here? What is one thing that we could do? Because there's actually two steps that we'll need to get to that point. So the goal is to get this term 2x minus 8 to turn it into simply x. Excuse me. So what is one of the two steps that we need to do to get that to happen? So we'll end up with a number where it's less than or equal to x, less than a number. Okay, well, let's look at that. So we have 2 less than or equal to 2x minus 8 less than 10. First thing we can do is add 8 to all three parts. The reason we would want to add 8 is to cancel out the minus 8 that's right here. So 2x minus 8, so we need to add that 8 to get rid of that, which means it has to be repeated here and here. So we add, that's 10. This cancels, so it's just 2x in the middle, and this is 18. Okay. So now we have 10 is less than or equal to 2x is less than 18. We already added 8. What else can we do to make this just a plain x in the middle? Subtract 2. Divide. Yes. Yes, we can divide by 2. And again, that dividing by 2 here, we repeat that here and here. And 10 divided by 2 gives us a 5. 2x divided by 2 is x. And 18 divided by 2 is 9. This is probably much less stressful than the future or present value problems or matrices. Yeah. So we actually do divide by 2, because this is a positive 2. We divide by the same number. We always, like with addition and subtraction, we always do the opposite. Like if it's 2x minus 8, we did plus 8. But if it's multiplication, like 2 times x, the opposite in this case is to divide by the same number, not by changing the sign at all. I'm not sure which topic you'll ultimately need this for, but it was on my list of things to cover, so I'm covering it. I don't recall the connection. It may be with the linear programming still, but that may be it. But I'm not quite sure why. But that's Chapter 7 material. So. And once we... oops. Ignore that one. Sorry. Once we have our solution, 5 is less than or equal to x is less than 9. We'll go ahead and put that onto our graph. So 5 and 9, and we'll shade between them. But again, this is less than here, less than or equal to on the side with 5. So we'll put a solid dot there. This is less than 9 on the right, so I'll put an open parentheses. Okay. All right. Another example. Let's say -3 is less than 2x minus 3 over 3. It's less than or equal to 2. I'm not sure what you're going to do tomorrow. It may be that you're done with matrices now, or that may be that you do a little bit more. I think, last Wednesday we looked at, problems from 6.2, so there might be a little bit more to do yet, so, yeah. If this is divided by 3, what is the opposite of dividing by 3? Multiplying by 3, yes. So multiply by 3 everywhere. So it's -9 less than 2x minus 3 less than or equal to 6. We can also, so next we have 2x minus 3, so with the minus 3 we would then add 3 to each part. So that's -6 less than 2x less than or equal to 9. And finally, we would divide everything by 2. Negative 6 divided by 2 is negative 3, less than. 2 divided by 2 is 1, so just x. And then 9 divided by 2, we could make that 9 over 2, or 4.5, whichever we preferred at that point. Just to simplify it to something we could put onto a number line. And when we graph that answer, or graph the solution, again, open on negative 3 because it's less than, closed out on 4.5 because it's equal to, less than equal to, and then shade everything in between. Okay. All right. Let's see. Next we have absolute value inequalities. Now when we talk about absolute value of x is the distance of the value x from 0. And when we say distance, this implies it will be a positive number, because we always measure distances with positive values. Okay, so if we look at, let's see, here's 0. We look at the absolute value of negative 4. We're saying how far is it from negative 4 to 0? 1, 2, 3, 4 places. So it's an absolute value of 4. If we say the absolute value of 5, we're saying how far is 5 from 0? Well, from 0, 1, 2, 3, 4, 5. So it's 5 places from 0. Now, probably you can already understand by seeing that what's actually happening here from a end result view is that if we have a positive number, the absolute value makes the number positive. If it's positive, it stays the same. If it's negative, it turns it into a positive. Okay? And so with absolute value expressions, whatever is inside is going to be made positive. Now, depending on what type of inequality we have with the absolute value inequality, there's two different approaches that we want to take. First, if the absolute value of x is less than 3, for instance, in this case it means negative 3 is less than x is less than positive 3. So if we have a less than sign, it turns it into a compound inequality. Okay. The second option is, of course, if we have a greater than number. Here we turn it into a pair of inequalities, which is that x is greater than 2 or x is less than negative 2. So rather than a compound inequality, we get a combination of two different inequalities. So when we say the absolute value of x is less than 3, that means that's every point that's less than 3 from 0, basically. Which means it's between negative 3 and positive 3. If we say the absolute value of x is greater than 2, that means we want every value of x that is 2 or more distance away from 0. So it's everything bigger than 2, and also everything that's less than negative 2. Because we're basically moving away from 0 in that situation. Whereas less than means we're looking inwards. So if we have a less than, then we create a compound inequality. If it's greater than, then we create a pair of inequalities. Now at this stage, there may be an expression besides x inside. And so if it was like absolute value of 2x minus 1 in absolute value signs is less than 3, then we would switch it over here, and they would still have the 2x plus 1 or 2x minus 1 inside here, and we'd have to solve the compound inequality from there. Same thing here, except we'd have two separate inequalities to solve. Okay. So as an example, if we have the absolute value of 3x minus 1 is greater than, let's say, 5. Okay. Anytime we have greater than, that means we split it into two parts. One is exactly the same as the inequality that we're given, just without the absolute value. So 3x minus 1 is greater than 5. And then we do 3x minus 1, and then we switch both the sign, or the direction of the inequality, and the sign of the number. So less than negative 5. So either 3x minus 1 is greater than 5, or 3x minus 1 is less than negative 5. That's always the trickiest thing, I think, is working with absolute value and inequalities at the same time. It takes a little practice to get used to that, and to recognizing which way we need to interpret this as far as creating a compound inequality or a pair of simple inequalities, like we have here. So if we have greater than, we end up with a pair of simple inequalities. If we had less than, we can make it a compound inequality. Okay. Because both of these inequalities have the same expression on the left-hand side, both of them have 3x minus 1, it'll actually take the same two steps to solve each of these inequalities. So we would start by adding 1 to both parts. So 3x is greater than 6, and 3x is less than negative 4. And the second step to get x by itself is to divide by 3. So x is greater than 2. or x is less than negative 4 over 3. And that's our pair of solutions that we would use there. Now when we plot this on a number line, here's our 2, here's our negative 4 over 3. So it's just greater than 2, which is everything to the right, but with an open circle. And less than negative 4/3 means, again, we have an open circle, but now everything to the left from there. Okay. So even though we split up the original problem into two different inequalities, because we are working one problem from the outset, our graphs need to be on the same number line. So basically, the only thing that doesn't work for this original inequality is everything in between negative 4/3 and 2. Those are the values that are being excluded. We'll then use everything on the outside from there. Okay. And for our other example, let's look at absolute value of x minus 3 plus 2 is less than 10. Looking at this problem, what do you think the first step would be? Will be the first thing that we need to do in this question. At 3? We can't interact with anything inside the absolute value until we break it out of the absolute value. Unfortunately, before we can deal with the absolute value, there's one other step that we need to do first. That's a good question to ask at this stage because I hadn't talked about that. But we can't mess with the absolute value until we get everything else fixed to where it needs to be. Now, yes, good. So we have this plus 2 right here. Let's subtract that 2 from both sides first. So we just have the x minus 3 absolute value by itself, and in this case less than 8. So I didn't mention this, so it was a bit tricky on my part, but we have to get the part with the absolute value by itself before we do anything else. Otherwise, it makes it we run the risk of making a serious mistake that affects the outcome. That we won't get a correct answer basically. Once we get to this point, again, we can't just add the 3 because of the absolute value, but we can break it out of the absolute value at this stage in the problem. We add the 2? We can only subtract because they're on opposite sides of the sign. In this case, we have an inequality rather than an equal sign, but the same processes hold true. I didn't see at which point you're at that comment. I'm sorry, Brent. Oh yeah, if this was negative with a negative 2, then we would add 2 to both sides. Yeah. Is that what y'all are talking about? Yeah, just whatever number this is, whatever we do, whatever the opposite is to move it over, like we always do. So it's just, opposite of +2 is -2. That's what we did. If this had been -2, we'd add 2 and then go from there. Okay. So now, because we have a less than sign, we can turn this into a compound inequality where x minus 3 is in the middle. Because we have an 8 on the right hand side, that means that x minus 3 is less than 8. And then we put the opposite of that on the left hand side, which is -8. Whenever we have, we may not have talked about this semester, but when we have it may be that we never talked about equations with absolute value. Therefore, inequalities is a little bit more weird. But I don't know that we ever talked about that. And may or may not be part of our sections that we looked at. It may be worthwhile talking about that as well. Time permitting, of course. I should have done it before this. Sorry. Anyway. Gosh. Because we have our absolute value of x minus 3 less than 8, I don't really need more followers. I just need my students to come to class. That's it. Unfortunately, that's one of the realities of Twitch, is that you do get this spam messages during your streams. I wonder if I could disallow certain words to prevent that happening, but I don't want to accidentally ban a student. So anyway. We can just ignore it and move on. I think that's the best solution. So to get x by itself here, we'll have to add the 3. And this time, because it's a compound inequality, we'll add the 3 to each part. So -5 is less than x is less than 5. 11. Sorry. Okay. Now we don't really do a whole lot with inequalities here, but I thought I would go ahead and mention them at least as far as how we would deal with it. But it did occur to me that we haven't talked about how to solve equations with absolute value, which is concerning. So let's look at that next. Oh, by the way, this on the number line before we move on is from -5 to 11 with a shade in between, basically. So with absolute value equations, an example would be like absolute value of x is equal to 2. Basically, when we see something like that, we're thinking Okay, what can we take the absolute value of and have it equal to? Well, there's actually two numbers for which that's true. Do y'all know what those two numbers are? Absolute value of 2 is 2. Good. And absolute value of 1 is equal to 2. That doesn't seem quite the same. It's not 1. 2 is correct for sure, but we need the other number that also has an absolute value of 2. So what other number, when we plug it in here and take the absolute value, will it be equal to 2 also? Let's remember what absolute value means. Absolute value means the distance from 0 is equal to 2. It's not just on the positive side, it also means on the negative side of things. Okay, negative 2. Absolute value of 2 is 2, and absolute value of negative 2 is 2. Both of these numbers, when we plug them in and take the absolute value, they have an absolute value of 2. On our number line, the distance from 0 to 2 is 2, and the distance from negative 2 to 0 is also 2. Okay. If we say the absolute value of x is equal to 7, what would x equal in that scenario? Seven and negative 7. Excellent. Right, because in this case, the absolute value of 7 is 7, and the absolute value of negative 7 is 7. Remember, the absolute value operator, or function, whatever you want to call it, takes a number and makes it positive, if it's not already positive. So if we plug in a positive number, it just leaves it alone. Absolute value of 7 is 7. But if we plug in a negative number, it makes it into a positive. So absolute value of negative 7 becomes positive 7 based on that. Okay. Here's a trick question. Can we take the absolute value of x and have it equal a negative number? It's one of those two. There's a little delay on my side as far as when I see the answers, so you actually typed in both of those answers before I had a chance to respond. You absolutely got it right. We just still need to know which one it is. So we talked about absolute value as being the positive number between the value that we have equal to and 0. So, is it ever possible to take an absolute value and have it be a negative number? If someone would like to commit to an answer. And it's okay if you get it wrong. We're still learning right now. Brandon's not ready to commit. Correct. It's actually impossible for an absolute value to equal a negative number. So in this case, this is impossible. And so what we would say is that there's no solution. Okay? So we cannot equal a negative number because by its very nature, whatever value we plug in here, taking the absolute value returns a positive number. It's never possible for a positive number to equal a negative. Therefore, there's no solution. Now, like I said, that's a trick question. We're probably not going to be running into those. I'm just speaking very generally about the topic of solving absolute value equations. Most of the time, it's like what we did in here and here, where whatever is inside the absolute value is either equal to the 2 or the negative 2. This is either equal to the 7 or the negative 7. Okay? That's generally the approach that we use. Occasionally we do see a trick question like this, but that tends to not be the problems that we test on. It's just for the completeness of the topic that we like to introduce it. Make sure we know the boundaries of what it is that we're talking about. Okay. So just to make it a little bit more involved, we have the absolute value of 2x plus 1. After that we have a minus 3, and then it's equal to 6. So there's multiple steps that need to happen here. In fact, there's at least 3. Probably a 4th one in there somewhere. There is one step that we need to do first, however. And it's actually a similar concept to what we covered with the inequalities, and that is if the absolute value is not by itself, we need to make it by itself. Exactly, we need to add 3, Brenda. Okay? So we add the 3 over. So we want to get the absolute value by itself first before we break it up into 2 equations from there. So the absolute value of 2x plus 1 is equal to 9. Now, we've gotten to this point. So we have our absolute value on one side by itself, equal to 9 on the right. Now we need to split this up into 2 equations. Now, from what we saw above, what could 2x plus 1 possibly equal here so that its absolute value is equal to 9? Okay, we're jumping a little bit ahead there, Gabe, but 4 is one of the answers, you're right. What I meant was, how do we break this out of the absolute value? That's correct. We're not dividing the 2x. We'll get to that. Brenda, I'm not... Okay, good. I wasn't quite sure what you were saying. Yeah, 4 is correct. That wasn't my... But my question is, not which values of x are going to work here, but in a general sense, how are we going to split this up to get two equations that we can then solve each one individually for x? And it goes back to what we're talking about up here. We said if we had the absolute value of x is equal to 2, then x is either 2 or negative 2. If we had the absolute value of x equal to 7, then x is either equal to 7 or negative 7. This time, if we have the absolute value of 2x plus 1 equal to 9, then either 2x plus 1 equals 9, or 2x plus 1 equals negative 9. Okay? There are, in fact, two solutions here, and I can see a lot of you are noticing one of the solutions, x equals 4, but we want to be able to get both. Not just x equals 4, but also the other one, which I believe is x equals negative 5. Okay? So we know 2x plus 1 equals 9. That's the equation that I think everyone is solving, and we're able to get x equals 4 there just by subtracting the 1 and then dividing by 2. Okay? The issue is we need to get the second solution. Okay? Which comes from the second equation, 2x plus 1 equals negative 9. So whenever you have the absolute value equal to a number, it's either equal to the positive or to the negative of that number. Because if this 2x plus 1 ends up being equal to negative 9, the absolute value of negative 9 is still a positive 9. Now we'll actually take the same two steps here. Subtract 1 first. So 2x is negative 10. And then divide by 2. So x is equal to negative 5. So in 4 and negative 5 are the two solutions here. Okay. Let's not worry too much about the absolute value. It may not be that we even need to worry about it. It may be that we never need to worry about that in this section. But I wanted to mention it because it's the second time it's brought up in the textbook. And I skipped the first time apparently. But don't spend too much time worrying about it. Okay. Let's go back to linear inequalities. And that'll be a better topic for us, I think. Now, before we talked about linear inequalities, it was really with one variable. But what we're probably going to be more interested in is linear inequalities in two variables. Now, two variables means that we're looking at having x and y in the equation potentially. They don't have to be there, but they could be. Okay, we have to have at least one. We may or may not have the second one. For example, we might say something like 2x plus 3y is less than or equal to 6 or x minus y is greater than or equal to 5. Both of those are examples of linear inequalities in two variables because we have two variables there. We could also just say x is greater than or equal to 3, or y is less than or equal to -2. Both of those are considered single variable inequalities, but part of this two variable setup. Okay. Because even though we're using two variables, we only use one in the definition of the expression. Now, the way that we handle this as far as being able to graph these things, we treat it almost as if we're graphing a straight line. Graphing a line in two dimensions. And this goes back to what we covered. It was in section 2.2, I believe. 2.1 or 2.2. We need to graph these and then shade accordingly. Okay? So for x greater than or equal to 3, we would graph x equals 3 first, then decide which side of the graph represented x being greater than or equal to 3, and shade in the designated area. Okay. So, the graph of x equals 3, what does that look like first of all? It's been a couple of days since we talked about section 2.2. Does anyone remember what the graph of x equals 3 is? Well, we know, yeah, we're going to shade past the 3 to the right, in fact, because it's greater than. Not a square, though. We know this is a line in 2 dimensions. All of these graphs will be lines in 2 dimensions. The question is, where is x equals 3? Yeah, we know 3 is over here, and if we say x is equal to 3, that is a vertical line. Okay. So the way that we graph x equals 3 is we find 3 on the x-axis, so that's x and that's y. We found 3 and then drew our vertical line there. That's x equals 3. That's what this line represents. Greater than or equal to 3, we'd want to shade To which side? Would the left side or the right side be greater than? To the right, yes. Okay. So basically, any coordinate that we pick in this shaded area, the x value will be greater than or equal to 3. And that is the goal. So if we said y is less than or equal to negative 2, it's really the same approach as what we did before, except because y is negative 2, that means we find negative 2 on the y-axis. So negative 2 is right here. And then we draw our line horizontally. Okay. Now when we look at the y function being less than or greater than, for y we always look at the top being greater than and the bottom being less than. For x it's always less than to the left, greater than to the right. So x is always like a horizontal measure and y is a vertical measure, is what it amounts to. And so when we say y is less than or equal to negative 2, less than would be everything below the negative 2 on the y-axis. Okay. Alright, so if we just have x greater than or equal to a number, or y greater than or equal to a number, or less than, or whatever, this is what we'll do. Let me go back to, let's look at one with 2 variables now and see how that changes. So with 2 variables, we could say, let's go back to the one I mentioned earlier, although this time, let's do a less than, and without the equal to sign there. Whenever we have 2 variables like this, we have x and y in the equation, or in the inequality, we want to write it in the form of y equals mx plus b. Now, the issue is it's not actually equals, though. It's going to be greater than or less than, just depending on how that turns out when you get everything moved over and solved for. But we basically want it in this form, our slope-intercept form, as we call it. Because then we can identify what the y-intercept is and then what the slope is, and use that to help sketch the graph. So it's going to get, again, be 2 steps to get it from here into this format. What would the first step be? Okay. First thing that we'll want to do to get y by itself is move the 2x over to the right hand side. So we'll just subtract the 2x. So 3y is less than a negative 2x plus 6. We could write these in any order, but preferably we would leave the negative 2x first. Okay. And then to get y by itself, we'll just divide everything by 3. So y is less than negative 2/3 x plus 2. And so this gets us into the form that we need it in, where in this case y is less than negative 2/3 x plus 2. But looking at this inequality, we can identify the slope and the y-intercept. Okay. Now that we know what the slope and the y-intercept are, we can use that to help us sketch the graph. We start at our y-intercept at 2, and then our slope is negative 2/3, so that means we're going to go down 2 and over 3 to the right. So we're going to down 2 and over 3 to the right. Now, you'll notice that instead of making solid points, I'm making open circles. Looking at this inequality, can you see a reason I would be making open circles instead of solid dots? It's because of less than, exactly. Because it's less than, it's not equal to. Since we're not equal to, we don't want a solid dot there. Less than is always just an open circle. Now, the other way that this impacts our sketch is that rather than drawing in a line through those 2 points, we'll actually make a dotted line through those points. So because we have less than in this problem and not equal to, like if it had said less than or equal to, we would say a solid dot and solid line, or yeah, that's good. Okay. The last thing we need to figure out is which direction we need to shade this thing. Because we have the less than symbol here, are we going to shade above or below? If it's less than, it would be below, right? Okay. Yeah, since it was less than, we shaded below. If it had been greater than, we'd shade above instead. Yeah. And that's one of the reasons we like solving for y, because it's then easy to interpret the inequality. When our inequality was in its original form, it's really hard to interpret what's happening when you look at this thing. But when we move everything over and we get it to where y is just less than negative 2/3 x plus 2, we can draw when y is equal to negative 2/3 x plus 2, which is the dotted line, and then shade accordingly with whether this is a greater than or less than at that point. Okay? So I think that, and we don't have any, I mean, that's not in this section. I wanted to go ahead and mention it just to get y'all thinking about that, is to go along with our other inequalities. That may or may not be something that we cover this semester, and if it's not, then we didn't spend too much time on it, hopefully. But I did want to introduce the idea, It might be something you run into in Chapter 7. So. Alright. I feel like we've done enough for today. It wraps up section 2.4. Do you all have any questions on anything before we wrap it up? Okay. Alright. I will continue to work to get the assignments ready, and I think that should help a lot as far as the understanding of this material. And I really want to get that done soon. It's just like I mentioned, it's been an issue getting in contact with Mrs. Knisley, but I will try again today and see if she does get back to me. So. Sorry about the complete lack of homework at this point. We'll get to it, so don't worry about it. Okay. If you see it show up in Canvas, it'll be there. If not, don't worry about it. So that's all I would say there. I know you don't really need any more work on top of anything else, but we need to have something to grade for this class, and so a little bit of homework would be nice. I'll try to keep it to 10 questions or less for everything, so it's kind of a manageable amount. So, alright. So like I said, we'll stop there for today. You all have a good rest of the week, and take care. I'll see you next time. Bye. Have a good one.